learners, I welcome you to this video program on oceanic circulations, tides part 2. In the previous video program, we studied about different types of oceanic circulations like waves, ocean currents and tides, and then we studied some detail about tides like how tides are originated and what are the different types of tides. We have covered different variations in terms of daily variations of tides and fortnightly variation of tides. Now let us study the other variations of tides like monthly variation, yearly variation and long term variation in the tides in this video program. And we will also study different theories related to the origin of tides, as I already told you that simply gravitational force of attraction of moon or sun is not sufficient to explain the origin and propagation of tides, and so there are some variations due to which we have different theories given by different oceanographers and experts in the field, and it is good to study them to know about different forces related to the origin of tides. Let us continue with the type of tides and let us continue with monthly variation of tides. As I told you that moon is revolving around the earth, and its orbit is not exactly circular one, it is elliptical orbit. So elliptical orbit has one major axis and one minor axis because its radius is not uniform. So at one point of time the moon is closest to the earth, and this position is called the perigee, which is about 356,000 kilometers, and at one point of time moon is farthest from the earth, that is 407,000 kilometers away from the earth, and this is called apogee position. And due to this there is a higher gravitational force when the moon is nearest to the earth, and we experience perigean tides, and it is about 15 to 20% higher than the normal tides. And apogean tides, when the moon is farthest from the earth, we experience apogean tides, that is which is about 20% lower than the normal tides. You can understand that distance between as the distance between moon and earth increases, so force is becoming lesser. So because as I told you that force is inversely proportional to the square of distance between two heavenly bodies. So if the distance increases between them, so force is lesser, so lesser force of attraction, so lesser height of tides. So this is in terms of monthly variation, we get perigean and apogean tides. And we also see half yearly variation, which is due to declination of sun, which varies from 0 degree at equator to a maximum of 23.5 degrees north and south of equator. And declination of a celestial body is actually its angular distance from the celestial equator on a celestial sphere. Now what is a celestial sphere? A celestial sphere is an imaginary sphere on the surface of which all the heavenly bodies or stars appear to be studded, and earth is considered to be at the center of that sphere. So declination of any celestial body is the angular distance from the celestial equator. Celestial equator is now the line protruding from the earth's equator and expanding up to the celestial sphere. So that is celestial equator. So declination of any star or a celestial body is its angular distance from the celestial equator. So sun's angular distance varies up to a maximum of 23.5 degree north and south of the equator, which is at 0 degree. Equator is at 0 degree and 23.5 degree north and south of equator. So based on this we get equinoctial tides and solstice tides. Both spring and autumn equinoxes, that is on 21st March and 23rd September, tidal bulge at equator becomes stronger, because during equinoxes sun is directly over equator. So, tidal bulge at the equator will be more compared to the normal height of tides, and we get these equinoctial tides. And what about these solstices? During winter solstice and summer solstice, that is 22nd December and 21st June respectively, sun's rays are overhead at Tropic of Capricorn during winter solstice, and on Tropic of Cancer during the summer solstice. So, places along these Tropic of Cancer and Tropic of Capricorn, these will receive higher bulge or higher height of tides, and these are called the solstices tides. So, this is half yearly variation. You can see 21st March and 23rd September is about 6 months apart, and then June to December, so half yearly variation in the type of tides. Now coming on to yearly variation, I have told you that moon is revolving around the earth in an elliptical orbit. So earth is also revolving around the sun, and this orbit is not exactly circular, it is also elliptical just as the moon's orbit, and then it is having a major axis and minor axis, as the radii is not equal at all places. So at one point earth comes closest to the sun, which is about 147 million kilometers, and this point is called perihelion, and it happens on January 3, and at one point earth is farthest from the sun. So it happens on July 4, and the position is called the aphelion. So when it is farthest, tidal force is lesser in comparison to the perihelion, and so tidal rise is also affected in that way, just as we explained the other type of tides. So during perihelion it will experience greater height of tides compared to the aphelion. Now there is also one long term variation. Absolute maxima reaches once in about 1600 years. It happens when earth, sun and moon are all in conjunction. Moon is in perigee, sun is in perihelion, and axis intersect with zero declination. An axis of all these actually heavenly bodies intersect with zero declination. Then what will happen when moon is also in perigee, sun is also in perihelion? Then tidal force would be phenomenal in such position, and now it is predicted to happen in about 3300 AD, that is pretty far from now, so we can just relax. And now learners, you should know about theories, different theories we have which were given related to origin of tides, and we have already covered some portion of equilibrium theory, or the due to gravitational force of attraction between the heavenly bodies, and this theory was actually given by Sir Isaac Newton in 1687. Then came the dynamic theory of Laplace in 1755, and then came the progressive wave theory of William Whewell in 1833. It is also similar to the canal theory that was given by G.B. Airy in 1842, and then comes the stationary wave theory which was given by R.A. Harris. Now let us study this equilibrium theory also in detail, because you have some knowledge of this, because we studied the centrifugal and centripetal forces in the previous video program. So the basic assumptions that were taken by the equilibrium theory is that earth is covered entirely by oceans. Water moves freely in all oceans, having equal depth and having no barriers, and tidal wave progresses with predictable time, having no standing wave component. Now let us understand this, that sun, moon and earth are all in equilibrium due to their respective pull towards each other, And as I have told you that suppose this is earth and this is the moon which is facing the earth at this portion. So, centripetal force at this portion will be greater than centrifugal force at this portion. Centrifugal force is the reactionary force to the centripetal force, and centripetal force is also called gravitational pull or gravitational force of attraction. And since centrifugal force is equal at all places on the earth's surface, so centrifugal force is equal, but centripetal force varies because on the surface it will be nearer to the moon. So, it will be higher on this surface compared to the center, and then compared to the opposite side of this surface. So, on this surface which is facing the moon, centripetal force will be greater than centrifugal force. So, it will experience a tidal bulge on this side. So, high tide would be experienced on this side, and exactly on the opposite side the centrifugal force will be greater, because centripetal force is much lesser compared to this, because distance between earth and moon would be now equal to the diameter of the earth, and then the plus the distance from the surface of the earth to the moon. So, greater distance it has to cover. So, centripetal force at this portion, that is on the opposite side of the earth, would be much lesser, and so centrifugal force, that is the reactionary force, here would be greater. So, this portion will also experience a tidal bulge. So, at a time we get two tidal bulge, that is one at this portion and this portion, and on the poles what will happen, the centripetal and the centrifugal force will balance each other, and the resultant direction of the force would be towards the center. So, at the poles we will have ebbs instead of tides. So, the water level would be lowered at this position. So, we experience two tides and two ebbs at one time. It may be stated that highest points of rise of water, or say high tides, lie nearest and farthest away from the moon, while the lowest points of water surface, or say lowest tides, lie perpendicular to the above places. So, these portions are having high tides and these portions are having the low tides. So, these are perpendicular to the above places. Two high tides and two low tides occur simultaneously at one time on the earth's surface. Limitations of this theory is that earth's surface is comprised of land and water and is not homogeneous, that is, it is not having water throughout, and the bulge of water may not be possible unless there is some horizontal movement of water, that the vertical rise of water will also involve the horizontal movement of water. So, how do we explain that? And the theory also this theory was a bit modified, and it envisaged that waves are generated during the occurrence of tides, and these waves move westward with their crest directly under the moon. But the time of high tide should be the same at all places along the each meridian, that but this never happens, because take for example Liverpool and Leith, both situated on 8° west longitude or meridian, but the time difference of the high tides between these places is about 3 hours. So, there is a vast difference, so how do we explain this variation in time? And there is a variation in the configuration of the coastal areas also, and ocean is not having uniform depths. So, tidal waves have to move under the influence of internal as well as external frictions. So, these are some of the shortcomings, and tidal waves are not free, but they are forced waves which are often obstructed by continental and oceanic barriers, and like continental margins and bottom reliefs of the oceans. So, another theory was given in 1755 by Laplace, which is known as the dynamic theory, who provided a mathematical explanation of tidal waves after taking into account both vertical and the horizontal movement of water. As the earth rotates, tidal bulge is generated by gravitational forces and starts moving horizontally towards the side of ocean facing the moon, thereby giving rise to the bulge of water. Obviously, when the moon is on this portion and the earth, this portion of the earth is facing the moon, so bulge is created by the horizontal movement of water, then only the bulge will be created or the vertical rise will be created. But as a result of pressure gradient, it moves in the opposite direction, which is further deflected by Coriolis force. And you must have studied about Coriolis force, which is force related to the rotation of the earth, and due to which ocean currents or winds are deflected to their right in northern hemisphere and to their left in the southern hemisphere. This is because of the rotation of the earth. Let me explain this dynamic theory with the help of this figure. You can see in all 1, 2, 3, 4 parts of this figure that the pressure gradient is created between high water and the low water, due to which water moves in opposite direction, starts moving in opposite direction and gets deflected due to the Coriolis force, and this way tides occur in opposite directions. Now another theory which happened to be more promising in explaining the origin of tides was the progressive wave theory, which was given by William Whewell in 1833 and G.B. Airy in 1842 also expressed similar views about tides, and his theory was known as canal theory. Now let us explain what assumptions were taken by this progressive wave theory, that the earth is a heterogeneous body and is not a perfect fluid, and tide occurs at different time and at different places on the same longitude. So it is trying to explain the variation in time of high tides along the same meridian, and there is a lagging of time of tides away from the source, and there is a variation in magnitude and amplitude of tides at different places, and tides is in the form of tidal waves which travels from east to west. Since earth rotates from west to east, so earth is rotating in this direction, so tides, these portions will come directly under moon, and so tides will move from east to west. You understand this? In the progressive wave theory, tides originating under gravitational force of moon in the southern ocean. It explains that tides are originating along the southern ocean, that is ocean area adjoining to the continent of Antarctica, where there is continuity of oceans and it is a homogeneous area. So tides are actually originating in the southern ocean, and they take the form of primary waves and then progresses towards the west, that is as the earth is rotating, they progresses towards the west. They are further stopped by the continental margins, and then they further move towards the north in the form of secondary waves. Further minor waves are generated from these secondary waves, which decrease in their magnitude and amplitude, of course. That is, tides are originating in the southern ocean, and these are the primary waves. They move towards the coast, towards the west, and then they are obstructed by continental margins. They move towards the north in the form of secondary waves, and then more minor waves are also generated, and in this way they are moving towards the north. So there is a time lag due to progression of this wave from the south to the north, and in this way this is explained that same meridian will have different time of high tides. So this theory explains this time lag of tides along the same meridian in this way. You can see in this figure co-tidal chart of Atlantic Ocean is shown. First of all, what is co-tidal lines? Co-tides are imaginary lines on the map drawn connecting places having same time of the high tide. So you see, first in the southern ocean you see it is moving towards the west, and because of continental barrier it is again moving towards the north, and then you see different time co-tidal lines are drawn further northwards, and this was actually drawn by G.B. Airy, and he said that more precise co-tidal lines were drawn along North Atlantic. That is why I have shown you this portion. You can also search in the map like co-tidal lines of the world. You can Google it and you can see good maps related to entire world map, and co-tidal lines shown that way. Now, what are the limitations of this progressive wave theory? The time of the spring tides is almost same. There are examples like from Cape Horn in South America to Greenland in the Atlantic Ocean, entire meridian is having the same time of spring tides. So, how do we explain this progressive wave, like how do we explain this time lag? There can be examples of time lag, but how we explain this, that the same time of tide is found, spring tide is found from Cape Horn to the Greenland along the same meridian. And besides, it was also suggested by scholars like tides are local or regional phenomena rather than originating in the southern ocean and moving progressively northwards. And spatial variation in the irregularity of tides in the different oceans is also not explained by this theory. Now, there was another theory which was given by Harris, which is stationary wave theory, and it explains the local differences in the timings and the type of tides. Tides are due to stationary waves which originate independently in each ocean. This Harris explains that it is not due to progressive waves which originate in the southern ocean, but it is more local phenomena, and it originates due to stationary waves which is originated independently in each ocean. Take for example a large tray of water and you stir it or give a jerk at one end, you see that the water gets disturbed and it starts moving up and down like this, just like a seesaw jhula. You can see, and the center portion of the tank would be stationary because it is called a node, and then water is rising and falling on the along the edges. So those are antinodes and the center is stationary. So if we consider all the oceans as major trays of water, so you see that these several amphidromic points along which water is stationary, but water oscillates around these points, and that is, water movement is nil in the center nodal point which is 0 wave height. From here water moves to a maximum level which is called the antinodal point. And once equilibrium is established, water moves up and down diagonally in open oceans. Water will move like this. So all places along these diagonals are called co-tidal lines. So there are several amphidromic points and water is moving diagonally towards the coastal area along these amphidromic points. So all these diagonal lines represent the co-tidal lines. And amplitude and the timings of tides are affected by local phenomena like the depth of the ocean, coastal and bottom topography, resulting into several amphidromic points in each ocean. Let me explain this. You can see in this figure, this right portion is shown that the amphidromic points and several co-tidal lines are drawn diagonally, and you can see in the left portion high tide, low tide along the edges, that is antinode, and the node is the stationary point. Now formation of waves which moves in anti-clockwise direction along these amphidromic points, and numerous stationary waves are generated from these amphidromic points which move towards the coast. And when these waves reach the coast, their crest and troughs cause tides and ebbs respectively. there is a positive correlation between the depth of the ocean and the height of the tides. Greater the depth, greater is the height of tide. Now in this world map you can see this is an open source world map which I have downloaded, and so I am showing it over here. You can see several amphidromic points are shown, and along these amphidromic points you see the height is almost 0. It is shown in dark blue, you can see, and then the co-tidal lines, the diagonal lines which are reaching towards the coast from these amphidromic points are actually co-tidal lines. And this is map drawn for the entire world, and you can see the amphidromic points, and as the height of the tide increases towards the coast, you can see it is shown in mostly green, yellow, even orange. So high tides, you can see that the coastal areas where the co-tidal lines are reaching the coastal areas, and they are forming a tidal bulge, and high tides are found in the coastal areas compared to the amphidromic points. So you see both stationary and progressive wave components are important to some extent to understand the variation in tides. Progression of water from amphidromic points can be predicted along each meridian, and water height increases towards the coastal areas as I showed you in the previous map, and these are modified by coastal topography resulting into different tidal ranges or tidal heights as explained earlier. So in this video program you studied about different types of tides, and you got a detailed description of theories of origin of tides. In the next video program we will study about oceanic circulation in the form of ocean currents in more detail. Thank you.